So in today's video, we're going to go ahead and continue with our basic introduction to integration. And so in today's video, we're going to actually look at how we can use kind of graphical methods and geometric methods to solve different integrals, very simple integrals over here. And so previously we looked at accumulation of change, and we looked at kind of what an integral really means in contexts. Now we're just going to look at general integrals over here, not really in a particular contextual application. And we're just going to see how we can use our knowledge of planar geometry, analytic geometry, in order to actually evaluate these simple integrals. So let's go ahead and actually do that. So over here, we have the integral from -5 to +5. I should mention these are all going to be definite integrals. So from -5 to +5 of the square root of 25 minus x squared dx, right? So these are our two bounds of integration. We have from -5 to +5. We have the integrand over here, the function we're integrating, which is the square root of 25 minus x squared. And then we are integrating with respect to x. That's what this dx, this little differential over here, is indicating. So what I did is I went ahead and I graphed out what this function would look like. You may recognize this as kind of like the upper half of a semicircle centered at the origin with a radius of 5. And again, that just comes from your basic like grade 9, grade 10 geometry. And so over here, what we can do is we can just think about geometrically, how can we use our formulas for area? Because we know that the integral from -5 to +5, I'm going to mark it over here. So this is -5 on our graph. This is +5. We know that this area is just going to be the area beneath the curve and above the x-axis. So it's going to be this entire area over here, right? And so the way that we can do that is we can just think about what is the area of this semicircle, right? It's the entire semicircle. And so if we were to draw the radius, right, let me clear this interior out a little bit. So we draw the radius. We know that the radius is going to be 5, right? We can also draw this as a radius. This is also a radius, right? And we know the radius is going to be 5. And we know that the formula for the area of a circle is going to be, we know that the area of a circle, let me write area of a circle, is going to be pi r squared, where r is our radius. And so we know that the area of a semicircle is going to be just 1/2 of this area. So it's going to be 1/2 pi r squared, right? Because it's a half circle, a semicircle. And so now we just need to think, what is our radius in this case? Our radius is 5. And so it's going to be equal to 1/2 times, and then we have our pi, of course, and then 5 squared, I should say, is 25. So this is times 25. So that's going to be equal to 25 over 2, or 25 pi over 2 would be our final answer. Very, very simple. Later on, we're going to look at how we can actually evaluate these integrals, using the actual integration techniques, using math, using calculus. Now we're just kind of going with a more geometric approach rather than a sort of computational approach. But still, this is a valid answer. 25 pi over 2 is the area is this integral, right? It's this entire area bounded by this circle above the x-axis. And then over here, we have another example. We have the integral from -4 to +4 of negative square root of 16 minus x squared dx. Again, these are our bounds of integration from -4 to +4. This is a definite integral. We have our integrand, which includes the negative sign this time. And then we have dx, means we're integrating with respect to x. So I went ahead and graphed this function out as well. This is, again, a semicircle, but this time it's the negative, or sort of the bottom half of a semicircle, if you're looking at it, on a plane due to that negative sign. This, of course, is going to be centered at 0. It has a radius of 4, so this is going to be -4 over here. This is +4, and this is also -4. And basically, the area we're asking for now from this integral is the area above the curve and beneath the x-axis, right? Because over here, our function is negative. And so if we want to integrate from -4 to +4, we're looking at this area right over here, right? We're asking for this area right over here, which is beneath the x-axis, right? That's the x-axis right over there. It's beneath the x-axis, and yet it is above this curve over here. It's above our circle. And so how would we solve for this area? Well, the way that we approach this is we would just calculate the area as we would be doing for a problem like this one over here, where we just figured out the area using our geometric techniques. And then when we figure out this area, what we can do is we can go ahead and take the negative of it. And the reason we take the negative is because we are below the x-axis in this case. So we're going from below the x-axis, and we're bounded by our curve from below. Meanwhile, in this example, we were going from above the x-axis, and we were bounded kind of above by our circle, right? And so let's go ahead and do that. So again, we know that the area is going to be equal to 1/2 pi r squared, right? Which is going to be equal to 1/2 pi times, the radius is 4 in this case, so 1/2 times pi times 16, right? Because 4 squared is 16, which is just going to be equal to 8 pi. So that would be our area. That's the area over here, right? The area over here is 8 pi, but this integral over here is going to be negative 8 pi. Again, later we're going to look at some properties of integrals and see why this would turn out to be negative. Now, kind of an intuitive approach is just whenever it's below the x-axis, then the area is negative, or the integral is negative, even if the area itself is positive, right? And so, in this particular example, we're looking at the area beneath the x-axis and yet above our circle, bound by our circle. And so we're going to be ending up with negative 8 pi as our final answer. Okay? This final example over here, the definite integral from -3 to +3. So these are our two bounds of integration. Our function is x, so it's just y equals x. It's the, I guess, the identity function, you could call it. And then dx, we're integrating with respect to x. If we were to look at this graph over here that I drew out, this is just an approximation of it. It's not very accurate, but so this is going to be -1, -2. This is -3 right over here. And this is +1, +2. This is going to be +3. So we're looking at this area right over here. We have two different portions. We have this section right over here, if it's gonna, okay. And then we have this section right over here, right? And so the way that we can approach this is we can just find the two areas and then sum them up, right? And again, later we're going to look at more properties in order to see how we can kind of split integrals into two separate definite integrals, right? So let's figure out this area first over here. So this is going to be -3 as well. This is going to be +3, right? +3. And so the way that we can figure out this area is this is just a triangle, right? And so this length over here is going to be 3. And then this length over here is also going to be 3, this length right over here. And so then we know that the formula for our area of a triangle is going to be, so the area of a triangle is going to be 1/2 base times height, which in this case is going to be 1/2 times 3 times 3, which is just going to be 9/2. But keep in mind, over here we're looking at the area above the curve and beneath the x-axis. So this portion right over here is beneath the x-axis, but it's above the curve. And so we're going to have -9/2 for that first portion right over here. So this integral would be -9/2. No, not 9 over pi, 9/2. And then over here, it's the same approach. Again, here we have a side length of 3, another side length of 3, and we want to find this area over here, but this time it's above the x-axis and below our curve. And so the area is, again, 1/2 base times height, which is 1/2 times 3 times 3, which is 9/2. But this time we're above the x-axis and below the curve, so we're going to make it a positive number. So it's going to be plus 9/2. But then what happens over here? It turns out that these two areas cancel out and we end up with 0 as our final answer. And if we're even looking at it geometrically or just graphically, this area over here kind of just visually looks the same. So this area over here looks the same as this area. And then we just have to remember that when we're below the x-axis and above our curve, we take the negative of our area. So that would be our integral. And then these two areas, when we sum them up, they'll cancel out. So just looking at it graphically, we can immediately tell that it's going to end up being equal to 0. But in general, this is just a very basic approach to solving very basic integrals using our general knowledge of geometry. And eventually, we're going to start delving into the actual properties of integrals and how to even evaluate these things using different rules.